This is the Amp Hour Podcast, recorded July 14th, 2015, episode 258. An interview with Bertrand and Gerald of Audeme.
Welcome to the Amp Hour. I'm Dave Jones from the EEV blog.
And I'm Chris Gamble of Contextual Electronics.
I'm Gerald Friedland of Audeme.
And I'm Bertrand Irisu from Audeme.
Hey guys, thanks for joining us.
Thank you.
Thank you.
It's an interesting topic we've got today, voice recognition.
I'm pumped about this.
Speaker-independent voice recognition, which is even harder than regular voice recognition, is it not?
Yeah, that's a good question. So, speaker-independent voice recognition these days is kind of the state of the art. So, there's different ways of doing it. One way is to basically have acoustic models pre-trained with many, many speakers, so that if you sound similar to one of them, it just works, and different speakers can speak, and you always sound similar to somebody else.
Right.
Yeah.
It's also what everybody's used to these days. Siri and Alexa and all these other systems that are becoming very popular are clearly speaker independent and continuous speech as well. So
yeah, I would expect that if Dave was speaking into the same device as I was, that it would recognize his crazy Aussie accent at the same time as my beautiful Midwest drawl. Well,
as a matter of fact, you'd be really surprised. We have tried on a variety of accents at our system, and I have a light French accent, at least I'd like to think so. Gerald has a German accent. We've tried on Indian accents and all kinds of accents of English speakers, and it actually works really well.
I don't know, mate. I reckon I can break it. No worries, mate. She'll be right.
Well, yeah, that might be an issue. There are some caveats.
Yeah. Another thing we should mention here is that so this is the Audeme and you guys are running a Kickstarter, and we'll get into all the details of that.
Yes.
But the interesting thing to me, the most interesting thing, is actually not the speaker independent, but actually the network independent. The fact that I'm used to having a phone. I talk to it. I say directions to 1234 Main Street, Cleveland, Ohio. And it recognizes that, but it's doing that because it's passing that audio file up to the cloud, processing it, and then sending back basically like a JSON or a text file basically to the Maps program. Then it's sending back text. You guys are able to do a localized recognition of that kind of thing. So how the hell are you doing that? I mean, how are you separate from the massive cloud that does a lot of the processing that people are used to?
So let me just go back to this issue of cloudless as we call it before we go into the technical detail.
Okay.
It's great to do things in the cloud. There's many reasons to go do that, but the reality is there's plenty of occasions where, first of all, you may not have a connection to the cloud, and we all know how well those Wi-Fi connections work. And I think the second issue, which is largely, understated, is just privacy. I mean, we all know, a lot of people don't seem to be terribly concerned, but I believe it's a real concern, privacy. And doing things local essentially get rid of this particular issue. You've got companies, a few months ago, Samsung got in trouble because their new TVs that essentially listen to voice commands was using a third party and sending unencrypted text or speech, to their third party for speech to text conversion, which basically anybody could have, eavesdropped on.
Right.
As a private citizen, it is of concern. So we really wanted a solution that was standalone. There's nothing that goes out of that board except, hey, I recognize sentence number 4 that you told me to recognize, and that's what it does.
Yeah, that's powerful.
Although I've got to say, Chris, you are a young whippersnapper, because I used a speaker-independent voice recognition chip back in early 1980s.
Right, and we all have seen your video.
You could buy it at your local... Yes,
right? You did a video about this.
Local Tandy store. Granted, it was pretty crap, and it had like 10 words, go, stop, start. You know,
Right.
but hey, it worked,
right.
and it was none of this cloud rubbish. Jeez, didn't even have to.
Right. Well, yeah,
but it
and
was
you could
very-
also
it was
say
very
that
primitive.
you could say that like, oh well, phones talk to you today, but then you could also say, well, the Speak and Spell was doing this. They were also it was electronics
The
talking to
Speak
you
and
back in the
Spell,
day.
yeah.
Like it's
Texas Instruments made a lot of money on that chip. Yeah.
Yeah,
Oh,
right.
they did. Yeah.
But it's just the levels of how much of that stack is really working for you, right?
Yeah.
It's a different experience, I think.
So the Speak and Spell is a synthesizer only, of course, right? So they were
Right.
not recognizing, but we were basically spelling and then would speak, which is an awesome toy, by the way. We still have that here. And I don't know where it is, but we had it like at least for, it probably still worked last year. And anyway, the reason why we can make it work is because there's a combination of sort of newly available chips that make this happen, and also basically the combination. And I mean, I've been working in audio and multimedia for 15 years, and there's basically just a lot of tricks you can do. Because it's not a dictation application, and it's basically voice commands, and so we can recognize full sentences, and it's also speaker independent, and you can program your own sentences, and a lot of this is happening by basically smartly combining lots of the stuff that is out there, and just making sure, and then timing is an issue. And there's a lot of things to just have to be right, and it's a lot of tinkering, but that's basically, it was a lot of fun to basically put this together, and as definitely as an acceptance to a challenge, because what happened here is that a lot of these companies were doing, Apple started, and also smartphones, even, and I usually say as a joke, the PlayStation 4 has a cloud-based speech recognizer, but the PlayStation 4 has like 8 CPUs in them. It's basically as powerful as some of the compute clusters that we use to do speech recognition on a research basis.
So
right?
what's the deal with that? That's
Right.
nuts.
And so they do it because then they have, full control over all this training and can update the models for new words and so on.
Yeah.
But what we wanted to do is we wanted to give that full control to the maker, to the, person that builds an Arduino project, so that they can customize it the way they want and they have full control over it. So that was the goal, and it's actually, again, I'm quite proud of that you can do that. You can totally program your own sentences, your own call sign. You can change all the timings. You can change, the responses, all of this.
And you can download those to the chip.
And you can, yes, exactly. You can upload these to the board, and it's training, basically the part that needs to be trained on board. And once you're done, you don't have to have an internet or a PC connection. It's just Arduino plus the shield. And you can build it into a robot, battery operated, and you may be somewhere in the wild where there's actually no internet. And we've shown some of these demos on the website, and also we presented it at Maker Faire, so people in the Bay Area, Maker Faire Bay Area, they could probably just basically try it out in live.
Right, which is where I saw it actually. Yeah.
Oh, right. Yes, you've seen the demo or heard the demo or. No, you don't hear it.
I enabled the demo with
you
my voice.
You controlled the demo.
My radio voice.
Please correct me if I'm wrong, but there are two types of speaker-independent voice recognition. One is the trained version, which you have to train before it can really do anything useful. And there's the Holy Grail, which is the untrained one, right? Which you can, you don't have to do anything. Anyone can just walk up to it and do things like the Dragon. Like a lot of people will be familiar with the Dragon software, right, which has been around since the 80s or something. That's been evolving. That's a trained-based system, isn't it? The more you train it, the better it gets at recognizing it and actually translating your voice into text. How does your one?
Yes. So I want to first of all, and this is not to be too professorial or too scholar, but we usually call it speech recognition. Because the voice recognition is what we don't want to recognize. We actually want to be independent of the voice because we want to recognize the words, right? No, it's actually very common, including marketing people do that. And in fact, we also, our Facebook page calls it Arduino voice control. But in reality, so the scientific term is speech recognition for that reason.
Got it.
So the question about Dragon. So if you have a dictation application like Dragon, this is much, much harder because you don't know whatever will be dictated, right? You're
That's
dictating
right.
full, maybe letters or
Yep.
full like papers even.
And it has
so
to be
there's-
100% accurate too.
Right, and
Otherwise, people don't get frustrated and don't use it.
Right, so it will never be 100%, but it has to be quite accurate so that
Yeah,
you
yeah.
actually save work compared to typing it, right?
Correct.
And so that's why they do speaker adaptation. So that means they have models for speech recognition in there, but they will adapt to your voice and make sure that the similarities they are matching are actually really, really similar to
Right.
your own voice. So the good news is that in our application case, we do voice control, right? So you cannot build a full dictation application with what we do.
Right, got it.
What you can do though is you can give it hundreds of sentences and sort of build a Siri type of application where you basically say, okay, like, I mean, we have these examples where we have Eliza, for example, or we have an adventure game, well, in early 1980s adventure game.
Eliza.
yeah.
That brings back
Can,
memories.
wait,
Sorry.
hold on, young person here. Can we get some help?
Young whippersnapper.
Yeah. Whippersnapper alert. Can we explain this?
Okay, so Eliza was oh my God, was it 70s or 80s? Well,
70s,
Okay,
yeah.
Yeah.
You can Wikipedia. So, but Weizenbaum basically came up with a thing where you would type natural sentences, a natural English sentence, and then it would react to it based on some keyword it spotted it. And it would basically emulate sort of a passive therapist, not a very good therapist, of course.
Yeah,
Just
it
a-
would talk to you and answer your questions and,
Right,
you know.
and
say-
Eliza, I'm depressed.
Right, pretty much. And the funny thing was that with very little AI, really, you could also almost fool people into it. And
You
of
could,
course,
yeah.
And of course, since the 70s, this has evolved to, I mean, some Elizas are really amazing at this point. It's like, oh my God, this is reacting to everything I say. And so it was really interesting for us to say, well, I don't like the typing. I actually want the real voice interaction. And so I did this with Movi, and there's a video on the Kickstarter page that shows that. And the other one is the Hunt the Bumpus game. So basically, it's a little adventure where you go through caves and you're trying to find this creature that is going to try to eat you. And so if you run into the cave with the creature, it's eating you and it's game over. But if you manage to shoot it first, then you win.
But the real purpose of these examples really was to show interaction, real dialogue interaction, where
Right.
you recommend either keywords or full commands essentially, and that's
Yep.
and that's really key. And Eliza, I mean, was essentially 40 lines of BASIC back in those days.
Yeah, I
know,
wrote
it
my
was-
own
it
Eliza
was- it
program in
was-
BASIC. Yeah, it's
Right,
great.
that's right. It was running into a 16K Apple computer, at
Yeah,
least in
that's
my
right.
days. And which is far less than any Arduino that you buy today.
Right.
And we just wanted to demonstrate that you could do all this just voice control using
Right.
the setup, and it's trivial to program. That's really the idea.
Right, and that's the point. It's like all of this can be done when if you basically pre-specify the sentences and the vocabulary that is to be recognized, which helps the recognizer tremendously, right? Because that's
Right.
what you cannot do in a dictation application. That's the big difference.
Got it.
Right, and it's almost like that the a lot of this stuff I think about in the sci-fi terms. Like this is the promise of the future is voice commands, not necessarily full. Like at least all of the sci-fi stuff is always commands of like, okay, Earl Grey hot, right? Like it wasn't like, well, I want it to taste a little bit waterier today, and I want it to be like a couple degrees warmer. It was always just a command. It wasn't necessarily
That's right.
a full
Right.
recognition type of thing.
It wasn't like going to Starbucks and really have a full range of options when you were ordering your latte.
Or even if it was,
I don't know.
it was still,
Hal
it's
was
still
pretty
bounded,
good.
Yeah,
I
Hal
don't
was
know.
good.
Actually, we should-
2001's Hal. Come
Yeah.
on.
You just gave me an idea for an application here. We should have the Starbucks voice control,
Yeah, well, yeah, and like all of
which
these,
actually would work really well.
right? I mean,
No,
you
I
have
mean-
all these K cups. You have these. There was another K cups thing where it was like a bartender. I mean, like all of these things. Like it's not,
Yes.
it's amazing when you think about it. When you move outside of natural language processing type stuff. Really, what we're really doing with even with computers these days and apps and all these other things, it is still command based. It's still click a button. A button is a single command, and in this case of if you can recognize a single sentence, as long as it matches that sentence, it's what you want to end up with the output. It's a digital 1 or 0 output kind of thing.
And that was exactly the intent that we had when we started this. I mean, you think of software programming as layers of programming. A lot of people don't think of hardware as a layer of hardware, but that's really what we're trying to do here. It's like, here's a board, give it a bunch of sentences, and it's just going to recognize them for you. And whenever it gets one, it just flags it and you do something with it. That's really the intent of this particular project.
Right. So when somebody programs this with the sentence, is that just programmed to them, or is it or does it try and be speaker independent for that sentence? How does that work?
Yeah, so you program the sentence by typing it. So you say in the...
Oh, okay, right. Oh, okay,
So,
that's clear. Now we're getting fancy-pantsy. Okay.
Right.
Definitely.
So that's why... So that was a complication we had, because, English spelling and English pronunciation really don't match.
Right. Yeah.
So...
it's a pretty crap language. Yeah.
Right. So what you need to do there is we included a 2 gigabyte, and that's the 2 gigabyte dictionary. Many people ask us about this. What does this do? So the 2 gigabyte dictionary is actually giving you type the word, and internally it's taking the word and mapping it to pronunciation. And this way, the movie board knows what to expect when you say the sentence. So that's also how it's speaker independent, because it doesn't know anything about the speaker anyway.
That's a massive amount of data, though.
Yeah.
How did you compile that sort of database?
These databases are online.
They're actually available, right? These have evolved over the decades, have they?
Yes, exactly.
Right. Okay.
This is where you need the speech research experience.
So when a user is using this board, does that mean that they're typing in something into like an online... So can you just walk us through the process here? Is it like the user types something? I mean, there's
Sure.
the Arduino sketch that I saw on the site, but does that mean it's going out to the cloud and actually grabbing these various pronunciations and downloading that whole thing to the board?
No, so the board has the board has a 4 gig SD card on which 2 gig is the dictionary. So the method through which we program the board, essentially, if you take an Arduino sketch, basically you have a setup, and in there you would essentially tell it, learn, sentence 1, I want to turn on the light. Learn sentence 2, turn all the lights off. Learn sentence 4, 3, 4, 5, etc. You can have as many as you want. Mm-hmm. Then you have once you're done with the setup, basically the board will go through its own learning phase, where basically it breaks down all these sentences into phonemes through the dictionary and figures out what to do with it. But that dark part is completely transparent to the user, and it's only done once if you change any of the sentences. Okay. And then all you have to do is in the main loop that you have, the main execution loop of the Arduino program, you just pull them on a regular basis, and you check to see if a sentence was recognized, and if you did, it'll tell you, hey, I recognize sentence number 4, and sentence number 4 was dim the lights 50%. Who knows? I mean, whatever you've programmed, and then you take that information and you go do something with it.
Nice.
On your board. So there is, it's all. I mean, literally, I think we figured the absolute minimum number of lines of codes you needed to add was like 5.
That's about as high level as you can get.
That's about as high level, and that's just to recognize a couple of sentences basically, and then do something with it. Really, really simple. I mean, it's extremely abstracted, if you will, but I think it becomes extremely intuitive to a user. And a lot of users on Arduino, I mean, they don't have 20 years of programming experience, and they're certainly not speech experts. So, and I'm not a speech expert either myself. So I really wanted something that was actually easy for me to use.
Well, that's why even back in the 80s, when we like the Speak and Spell and the famous SPO 256 speech allophone chip, right, which would actually talk. Right, it's not voice recognition here, but it was actually difficult to use that chip because you had to know all about phonemes, right, and you had to know how to concatenate them together to form speech. So that's why they came out with this companion chip that would just take serial ASCII in, and then it would figure out all the allophones for you and generate the speech.
Exactly, so, and for us, so the board also has a built-in synthesizer as well. With both male and female voice, although the male sounds a little bit like Stephen Hawkins. But the idea there is, there's a say command, and you just type in plain English what you want the synthesizer to say. And again, we use the same dictionary to phonetize and make it go through sound. So trivial to build dialogue, basically.
I was going to say, so you almost got that for free. You almost got the capability for free.
Yes, that's correct.
Right, nice.
Can you guys explain the phonemes a little bit more for uninitiated like myself?
Sure.
Just like what they are and how that ends up affecting some of this stuff. Obviously, Dave made a video about this, and I'll link that in as well. But just kind of how all this stuff fits together with the segments and breaking up speech.
Yes. So pretty much what it is all words in all the languages, but let's keep it to English, are composed of. So like we have 26 letters in the alphabet. We have sort of a set of phones and phonemes in each language. So the letters in the alphabet, especially in English, only roughly correspond to the phonemes. And so what you have to do is you basically, there's phonetized alphabets and so on. So the point is, phonemes are basically like the letters of the language, except they're really corresponding to how we pronounce the language.
Can
so
you give
like
some examples?
A is a phoneme, right? And this is of course repeated in so many words, right? So it's like some unit that is like the minimum unit that is repeated.
So you mean A being not the letter, but the sound like AY if you were spelling it, right?
Exactly. So and A is different, right? While the spelling would be probably the same. In English, you never know, but it would probably be the same, Well, but T, K, P, these are also meaning bearing, and so when they bear meaning, that's when they're called phoneme. And when they're just basically a random sound, it's called a phone. So there's also it gets tricky at some point.
And it's not just a matter of joining them together. You also have to add little delays here and there, right? As well.
Right. So and also then depending on the language you're using, there is of course like sometimes it makes a difference whether the stress is on different syllables, right? And stuff like this. In English, we don't have that much. And then, of course, if you ever do Mandarin, there's tonality in there, so it becomes tricky.
Oh, right, like ups and downs and diphthongs and all that other stuff, right?
So exactly. So that's why for now, by the way, people often ask this: is there how easy it is to do other languages? It's not that easy. Right now, we keep it to English, and if there's enough demand, we might actually take on the challenge to do other languages.
Do you guys do Esperanto? Any Esperanto?
No, we don't speak minions. I'm sorry.
Right.
Not yet.
Not yet. You'll get there. Yeah.
Not yet. You get there.
The one thing we really tried really hard to do, we wanted to do a really, really good quality, project board, because there's so many things that are really just average out there. We really wanted to kind of up the ante on the result. And as soon as we start focusing on it's only two guys right now. It's Gerald and myself doing this, and we just don't have the resources to go, to do more. If there's interest, we'll definitely look at other languages. We've actually had lots of requests for, German. There's some interest for Spanish and French as well. These are sort of the easy European languages, if you will. I'm sure there's plenty of opportunities for others, but again, let's do the first one really well, and then we'll do the other ones afterwards.
Yeah, that's smart. Yeah, that's good.
Now, you guys actually, we should talk about this. It's a custom chip, right?
No, it's not a custom. It's not a custom chip. It's not. It's a company called Allwinner. It's a Chinese.
Oh, right. I thought you actually used them as a like to actually do the custom chip for you.
No, it's a general. Oh no, God, that would require a different amount of financing.
I was going to say
this would be a major Kickstarter campaign there.
Exactly.
This is $1 million
I was going to
Kickstarter.
ask about this. Yes, how has this come about? Right. So you're using this off the shelf chip from Allwinner. Is that right?
It's actually that chip is used in a lot of tablets and portable electronics on I guess non-Apple and non-Samsung products.
And what does the chip do?
Well, the good news about this chip is that it's initially designed for tablets, so it has a whole CPU in there, so first of all, and then second, it also has audio input and audio output, because tablets usually have that.
Yeah.
And that makes it very, very convenient to use.
Yeah, so it's low power, it's fairly inexpensive. It's an ARM Cortex 8 inside, so it's quite a powerful CPU.
Oh, I see it now. Yep.
Yeah, and that's the same company that was used in the chip, the CHIP, that $9 quote unquote board that's on Kickstarter now as well, right?
Is it the same one?
That's right. Yeah, that we're having. Let's not get into this. I think
of course.
Yeah.
But it's the same company at least, and that's basically
right.
what I'm trying to get at. So
they're actually a major player. They're actually one of the largest. I don't know if I should say that, but largest customer of ARM.
Yeah, no. I mean, yeah, it's in lots of consumer level devices. I know that.
Oh, very, very, very reputable company. Actually,
Yeah.
it's not very well known by consumers, but
Right.
people in the hardware know them.
We had an article on our subreddit where we keep our links this week about because Allwinner just came out with an 8 or so you guys are using the 813, correct?
Yeah.
Yes.
They also just recently released a 820, I think, or they announced the
that's
820, something like that. So, yeah, it's very interesting to see this stuff because it seems like, especially with Allwinner and these kind of similar consumer level chips, these are the ones that are just moving super, super fast. And I guess tied to that, does that end up affecting you guys because you're using this chip? Is it going to be here in 6 months? I mean, or does that even matter?
So the answer is yes, the chip is going to be there in 6 months. We've actually had discussions about this. Actually, that particular chip is used all over the place. So it's actually made, I think, by TSMC. And basically, as long as there's demand, they will keep. As long as there's demand and as long as the process is available at TSMC, it will get manufactured. You might have to go and buy 35,000 at a time, but it's definitely available.
Right.
Now, the really good news, if you look at the architecture that we're using, the underlying of what we're doing is really a Linux. We're running Debian on it. We did a whole bunch of things to have it boot in a couple seconds. So really, if at some point it's very certain that this chip will not be available, but we'll have to go and use one of its future brother. It will probably end up with a redesign of the board on the next generation, and recompile and keep going.
Yeah.
So
That's not really a showstopper.
That's the benefit of doing high level programming like that. That's great,
Exactly.
actually. Yeah, that's awesome.
And it's really a hybrid of low level and high level if you think about it. I mean, it's high level in a sense that we are programming at higher level. It's low level in a sense that we kind of control the hardware. So and we like the idea of having just that running on that board. It helps us control timing. It helps us control all kinds of things. I mean, you're doing real-time speech recognition. You want your system to react in 300 to 500 milliseconds. So you don't want, all of a sudden, a service interrupt, servicing your screen,
Right.
or you dizzy, and all of a sudden the system become unresponsive. So that's one of the advantage of controlling the hardware.
Definitely.
Is there any? Would your ultimate goal be a custom processor? Like, say that there are other speech recognition, voice recognition chips out there, like the the HM2007 or whatever it is. Ones like that. Would you want to go for a custom if you could? Is there any huge advantage to that?
I have 25 years of doing chip design and custom chip designs.
Yeah, right.
And the answer is absolutely not. Unless you're going to be selling millions of systems.
Right,
So
yeah.
there's a threshold. Doing a custom chip of something like this is a
Of course.
multi-million-dollar undertaking. If somebody shows if someone shows us that there is a $50 to $100 million opportunity out there for doing this and is willing to finance us, hey, we'll gladly take their money and go and run with it.
Right.
Yeah.
But we're not there today, and we're taking it one stride at a time.
It just seems a shame that everything goes high level. Oh yeah, let's just do it in a Linux. Let's just do it in an ARM processor running Linux. Yawn.
Yeah.
Well,
but there's good company there though. My cell phone actually. I think it was one of the first ones doing it. Maybe not. but I know that the Moto X, I have a Moto X, and it runs a coprocessor just sitting there listening for voice commands, and it's the same thing where it's a high level. It's just they don't like have a custom processor. I think they just doubled up the processor.
Right. Okay.
I could be wrong about that, but
To be frank though, that is the appeal for makers too, right? I mean, what I like is when I saw this first, that really reminded me of the Commodore 64, really, where you have, you had your basic, but then you had the peaks and pokes where you could directly access the hardware. And in some way, it's the same thing, where right now you have GPIOs and you can actually, turn on and off individual lines. And I mean, you could, some of the chip, for example, is double the 2 or 3 functions on the same output pins, and so you can actually switch those functions, which is kind of interesting. We actually had to do this as part of the development, and then you could create a custom kernel. For in our case, for example, there's no TCP stack in it because we don't have internet on the board again, and so on and so forth. So you go very, very low level, and at the same time, you can run a Bash script or a Python thing on it. So you have the full range of capabilities there, and you own it, which is really interesting. And as far as I know, also the A13 itself allows bare metal programming, so you could actually do it without Linux.
Right.
Right.
That's killer.
But it's still not power and size optimized for the task, though. But to do that requires full custom and millions of dollars, as you said. So.
Yeah, it's a $1 million undertaking basically that can be justified if you're targeting particular markets, and I think it's going to be really interesting. I mean, I think one of the outcome of what Gerald and I did is we're showing it you really can do it, and you can actually do a pretty good product out of this that could literally be in a lot of devices.
Right. Cost
is an issue. When you look at the kind of bill of material, raw bill of material, and I'm not counting everything, you're talking $10, $12. Of stuff in medium quantity, might be 20% cheaper, 30% cheaper if you're building millions. But even if it's $10, you really, it's hard to justify that additional cost to a toaster. Not that I won't necessarily talk to my toaster, but at $10, it's going to be adequate for some applications. But it's going to be way too expensive for other things. I think that's the reality. Yeah. So at some points, once people realize, oh my God, we can actually do this, if there are people out there who want to come talk to us, hey, we'll gladly listen and work with them to do something like this. But the first step was really to show people. First, it can be done, and it can be pretty cost effective for a lot of solutions. And yeah, I'm sure we can make it a lot cheaper. But
yeah, $10 is killer. I mean, that's a really like $10 for a robotics project is nothing, right? I mean, that's a servo.
That's the bomb. That's the bomb. That wouldn't be how much the thing is sold for.
But even still,
you still have to do everything else. But that's the incremental BOM bill of material for somebody who's already doing a board and the assembly and everything else would be of that order.
Right.
So yeah, it's a pretty cheap add-on, really.
Yeah.
So is this all open source? Is this open source hardware, or are you guys actually starting a company and the technology is proprietary?
So we're actually using a lot of open source software to do all this.
I'm more talking about like the algorithms and everything else.
So all the algorithms are open source. There's a lot of packages we're using. We're actually going to put everything on the site once we actually release the product, because first of all we have to, and we want to give credit to where it's due. A lot of the know-how is really how you put all these things together and getting it to work. We're not entirely decided yet how much of it we want to share at this point. And the hardware itself is fairly straightforward. I mean, it's basically
it's a big ass processor with
it's a big ass processor with
memory.
half a gig of memory and a 4 gigabyte SD card. Okay, well, there you have it. We're going to a conference next week, and we're showing what it is exactly. So there's really no secret there.
Right, and that will be ESC. We should mention, because some of our listeners may be going.
All right. Yep.
That's right. Yeah, in Santa Clara, California. And so at this point we're not open sourcing the actual flow. That's the one limitation we're doing.
Right.
That's okay. I mean, everybody's got to make the decision about where you're going to make the money, where you're going to make the decision to be open or closed. fine with me. I mean, like, you guys put a lot of work into this, so so when you say open or close, though, like, so when you think about this into the future, and we talked about the BOM cost as well, do you envision this being always, like, do you envision licensing this out as a like, buy this processor, have the software stack, you're good to go, you basically pay a license fee type thing, or how do you envision it working?
So, yes, that's the next step for us in some respect. I mean, some people, there's really two types of users in at least in our experience. The one that just want, here's the board, I call them the system integrator. Basically, it's like, oh, I've got this great idea, and I just want to buy a board that does this, and they don't really care about saving money there, really, if you will. But the other model is to license essentially the stack, and basically have people talk to us. We'll show them exactly how it's done, what it takes, how to implement it on whatever platform you have.
Put this processor on your board, put this other stuff, and then install this, right?
Exactly. I mean, basically, we'll be holding their hands. We have the expertise, and literally in a few days, we can get this up and running on your particular Linux distribution, or on a core of your, a Snapdragon from Qualcomm or something like that. I mean, there's plenty of ways you can do that.
How much processor grunt do you actually need? Do you actually need a big ARM Cortex A8 or whatever it is, and working at gigahertz or hundreds of megahertz? Can this be done like lower end? What's actually driving the response time there?
Couple op amps and like some TTL logic, or what are we talking about?
So the answer is yes, but at what quality? And so the way I did this,
quality.
Someone is speaking. We know this much. There's definitely sound going on.
Right,
is it a dog barking? I'm not sure.
So I mean, you can build a board that just to, let's say, discriminate between yes and no. That would be not hard. Maybe even speaker independently. That would be not that hard. But we do really. I mean, we can do hundreds of sentences, and we give this soft limit there, 200 sentences, which is our limit. Like, this is where we stop testing. If people manage to put on more, we have no restriction on there.
Right.
And the major point is that we have a lot of models in there. So we have the acoustic model, which is basically matching these phonemes. But then there's also a language model in there. So basically, we built the language model based on the sentences, so that when you recognize a sentence, when you say a sentence, that it's similar to another sentence. Based on the similarity, we can still match it, for example. But then also the point is that if it doesn't get it 100%, it will try to match it against the sentences it has. And so there's this acoustic model, a language model, there's a matcher. And if you combine all these two, then you get the quality up. And of course, the more you add models and the more you add algorithms to make it better, the more you need CPU. And
because it's a brute force type approach. Like, if you've put in 200 sentence commands in there, it's got to search all 200 until it finds a match, or is it more advanced than that? Can it narrow down the options of which ones to search?
So there are two ways. Actually, we give two options to the programmers. One option is to do the raw recognition. So, for example, if you train it to recognize 1, 2, 3, then you can recognize 231 or 223 or 113 as well, right? But the language model will favor 223 in some way, because if it basically says 22, it sounds like 3, then it's going to be 223. And so the other thing, though, is this is the first model. We call this raw output. It's very, very useful for passwords, for example. If you actually want to ask for a password, you do it this way. The other mode that we have is you say, no, I actually want an exact match. And that means for all the sentences you put in, if you say 224 and the only other sentences that has 2 twos in it is 223, then we'll force match it to 223. Because we say that's the closest one, right?
Does this mean that the higher likelihood of success for programming this as a user would not be to have single words, but instead to have sentences, because there'd just be more matching criteria against a sentence versus a single word?
Yes, and that is the beauty of language models. So in fact, if you say light on, light off, because it's just on and off, these two words are very, very similar. Like there's really just one phoneme differentiating it. It's way harder. But if you say, make it bright versus I want to sleep, it's going to be, basically 100% accurate. Right?
Yeah.
And that's the beauty of language models.
There's one thing I want to touch on. You were talking just earlier, because I'm not sure we quite answered your question regarding the CPU power. There is one very important thing, which is the overall response time. So we don't use 100% of the CPU, obviously, but when we do recognition, we want a quick answer. So if you're actually having a dialogue with, or you're talking to the board, and you want to answer, we expect a, half a second response time, basically. If you have to wait 5 seconds for the board to decide what it heard, it's unbearable, and it's completely, I mean, the human interaction is horrible. So we need that amount of power to essentially get that response time, which is within a very acceptable human interaction expectation.
Right. If you had a butler, you'd expect about a half second as well, right?
Yeah, exactly. I mean, you don't want to feel like you're talking to somebody who's on the moon and have a 6 second, response time.
Where is at what? Is there something that's a real bottleneck in the software to the processing time, or is it just a whole combination of a whole bunch of things?
It's a whole combination of a bunch of things. But also, since we allow training, when you pass it 200 sentences. Right now, you have to wait 20 to 30 seconds. So that training process takes long. But again, the training process is only done once, sort of, when you change the sentences. Basically once per project, sort of, right?
Got it.
Or if you update the project. But in reality, it's we want to have a smooth response. And like everything else, like, for example, if there's more noise, you have to take care, the processing takes a little longer and so on. We want to just basically be able to smoothly respond to whatever comes in there.
How do you deal with echo and things like that? Like if, you've got an omnidirectional mic on the board and somebody's, all the way on the other side of the room shouting, and the rooms, there's not much furniture, and it's echoing like
podcaster talking here.
Yeah, you guys are audio guys, I can tell. So echo is an issue. So what we did is actually we put a lot of care. The board we're doing is more than just a computer board. We spend a lot of time on the audio front end as well. We wanted a system you can actually talk from, a distance that would work from literally a few inches away to about 12 feet or so. It really depends on the room condition. Now, ideally, you don't have echo. We don't do echo cancellation. The onboard microphone is just an electret microphone. It's it's fairly broad in terms of its pickup. It's omnidirectional. We don't do echo cancellation. So if somebody had an application where there is echo, one of several things is going to happen. Either it's going to reduce the range at which they can talk considerably. Literally, they might have to be just a couple feet away when you talk to it. That's a real issue. Alternatively, we offer, they can actually put you can put an external microphone and bypass the internal one, and then you could put an array of microphone that does echo cancellation, basically.
Right.
But this becomes very project specific, and so we can't solve every single problem. We kind of went for I would call the most common case there. We think it's going to work. It's going to actually. It's not that we know. We've tried it in a lot of conditions. It works really well. There's cases, for instance, where loud environment. When we were at Maker Faire,
of course,
the average,
the average,
we had a dB meter that recorded an average of 82 dB constantly. So there was absolutely no way you could talk to it, at 12 feet. And here we had to use a headset. But with a headset, it worked. It worked perfectly. I mean,
of course.
Actually, to tell you the truth, we were a little skeptical at first, and then we're actually very pleased how well the audio front end responded to that. And I mean, Chris, I'm not sure if you got a chance to try it there. But
I did. Yeah, I did. So can you tell us a little bit about the front end? I mean, is it all built into the silicon on the A13, or is there external op amps?
No, it's external op amps, basically doing good automatic gain control and other things as well.
So what kind of op amps? I mean, like what's on board? I mean, is it just an ADC or the AGC auto gain control op-amp, basically?
Exactly. We're using a good quality AGC to essentially, I mean, the idea is you want to be able to pick up something that's in a quiet environment. You want to be, pick up the sound. So the basic principle there, when it comes to audio, especially speech recognition, is, garbage in, garbage out. If the signal that you're getting in is terrible, your speech recognizer is not going to do anything good. So you have to get good audio input and try to essentially normalize it. The advantage of doing it in analog, if you will, is that you get a very, very fast response time. So if somebody starts shouting, you adjust, immediately. A lot of the ADCs that these built-in CPUs have are fairly low quality. They can do 1 or 2 bit of adjustment, but it's 12-bit. It's not going to give you any kind. If you had a 24-bit, ADC in there, you might be able to. You probably would be able to do it digitally, but that's not the type of what we have.
So are you willing to tell us what the part number is, or do we have to wait for Dave to do a teardown for this?
You'll have to wait till we get the board out.
Come on.
Yeah, I know.
We're gonna get there. We'll get there.
Well, you'll get there. You'll get it soon enough.
Okay. So some form of the audio AGC.
Exactly.
I've had bad experience. So Dave knows this as well. But both Dave and I have an H1 recorder for audio stuff, and the auto gain on that thing is terrible. I don't know if it's just I think it might be a digital algorithm type of thing where it's so discreet. It just steps it up. It's like you hear it when you listen back to the recording. It's like hello, this is Chris, and I'm now in a bathroom, and blah blah blah. And it's just like it's terrible. It's just like it steps up like that. So how do you deal with that? I mean, is it gradual?
Yeah. So the issue here was actually quite some work to figure this out, especially against the closed circuit that we don't know from A13, because A13 has a microphone input, and we didn't know anything about it. I mean, if you find something out about it, please tell me.
You can't just go listen to it, right?
So I remember several oscilloscope sessions that we had on this, and we also like trying this. And the other problem that we have is that. So now you distort the signal, right? Because while it sounds good to humans, speech recognizer might not pick this up so well.
Right. So
there was a lot of testing involved, and this is partly why Bertrand is saying let's wait a little bit, because we're kind of proud of this solution. So that was actually hard. That was a hard part. A couple of months of testing until we got this right, but it was totally worth it. So I mean, the robot example, for example, that you see on the video that we just posted with Romibo would not have been possible without that part, because when we have, and in this case, like the microphone is inside the robot and there's a fur around it.
Yeah, right.
And the person
that's a nice windshield.
Yeah, exactly. It's a high pass filter.
It really is, actually.
Yeah, right there, right?
Yeah, it's a totally excellent dead cat built in.
While that is kind of true, the thing is you don't really need a windshield when you're inside, and you're actually you're just sort of 12 feet away, pretty much where he was, and just said, Romibo, come here, and it just works. And in some ways, I'm always surprised myself that how well that worked. But it was basically the result, and I totally texted this to Bertrand. It was totally the result of us fiddling with it until we got a nice audio front end.
Mm-hmm.
What frequency response do you need for speech?
Yeah, so
that's a good
speech
question.
Recognition. Is it the classic 300 hertz to 3 kilohertz phone bandwidth?
10K. You need those hard consonants, Dave.
Tell us, come on.
Tuz.
I tell you no. So no, I mean. So that was basically telephone speech a long time ago. The 3 hertz to what we have is we usually, first of all, we sample at full rate, which is 44 100 or so, at basically CD rate, because we can, right? Because we can.
Right, of course.
Right?
But we're talking about what is the minimum requirement.
But all the models and everything is usually in speech recognition is now trained at 16 kilohertz sample rate.
Right.
And that gives you like sort of a 50 to 8 kilohertz, sampling frequencies that you basically can pick up, and you need those higher frequencies for distinguishing of S and T and so on and F.
F, yep.
And actually F is so important. Turn off. You really need that.
Yeah, the trailing stuff,
important.
Right? Or start.
It's very important.
Start instead of star, it's start.
Yeah.
Right. That's
and
the
for
big
guys
difference.
like me with a high pitched voice.
Yeah. Right.
Well, yeah.
Right. Yeah.
So actually, you're bringing pitch, which is really interesting. So the models we're using for training are actually all adults. I mean,
Yes.
we're trained by adults, and so what we've realized, and it's interesting because we're targeting at least the maker community, and there's a lot of kids there.
Yeah.
And it's a great the board is really great at telling boys ages, because essentially if they haven't hit puberty, it doesn't do very well. For boys, they really have to get that lower voice to really get things to work. So it seems to not work very well for boys under the age of 12. After 12 it works great, but for girls it works at much younger ages. So girls, usually 8 years old and older, seems to work without a problem. It's very interesting, and it's just, and it's not that it really has to do with training more than anything else, because the sampling is adult voices for all kinds of legal reasons.
So one thing I also wanted to ask about is the so you mentioned response time previously, and you said about 300 to 500 milliseconds. What actually is that stack up? Can you tell us about the okay, so from the time when that 50 hertz to 16 kilohertz hits the microphone, goes through the AGC, very minimal delays from there, it gets into the ADC, what happens then? Like all the way up to the top level?
So I mean, basically, the kernel of the operating system sends us the sound data in packets, right?
Okay.
So is it is it as the person is speaking, or does it wait until a pause at the end of a sentence?
No, as
and
the
then
person
processes?
it's sending packets constantly, right? So you have
Constantly,
to react to
right?
these packets
Okay, yep.
all the time.
Right.
And then the first thing you need to figure out is the person speaking. In our case, what we'll do is we do this energy based, and there's a fixed threshold built in, but you can also modify that threshold.
Okay.
And it's actually it sort of tries to be a little intelligent, because we know we have a model in there that knows how language typically works. So we, for example, know that if it's something super short, like it won't be a word, right? Did you hear that actually?
Right.
Yeah. Okay. Good.
Okay.
Or if it's like ongoing, never changing for 10 seconds, that's not a word either, right? So there's some intelligence in there. Actually, that's yet another model that needs to be calculated. You usually don't even mention that one.
So can you give us like an example? Be like someone saying no, like curtly saying no, or someone saying like screaming like ah. Like, is that like kind of the difference you're talking about, or what?
That's the difference I'm talking about, yes. So, because usually words are like sort of half second or good of a like half a second long to like 2 seconds long, right? Depending on the long word. Germans have very long words, but we do English. Right? And then also there's some short pauses, and then there's longer pauses, and these longer pauses really usually indicate somebody's done with speaking.
Okay.
And so you have to catch up to typically how dialogue works. This is also something we can do in contrast to when you have systems that try to transcribe stuff, because we talk to the machine, and in fact there's always a little bit of an adaptation going on of the human towards the machine. But this works pretty well. I mean, you see all the examples that, they work with that. And so once we have figured out, okay, so that's likely some speech, we'll basically need to recognize this. And in order to recognize this, we extract features, and then we use acoustic model to try all combinations of phonemes that this spectral envelope could represent.
Right. I was going to say, is this done in a spectral form? Do you like FFT this, and then you look at the spectral density in each frequency band? How does that work?
Sort of. So what we use is what everybody uses these days is MFCC features. MFCC features stand for Mel Frequency Capstral Coefficients. And capstrum is an interesting word that is actually like spectrum except not, right? This is kind of weird, right? And if you look that up, actually, that's very interesting. That's exactly what that is. So what it is you do basically you take the logarithm, then you do an DCT, and then you do what's called a MEL spacing. That means you weight the frequencies according to typical hearing. So like lower frequencies are perceived differently than higher frequencies, and so you basically do this weighting. And then, and that's the interesting part, you do a DCT again. So you take a DCT of the DCT, and this is a total hack, right? So
and DCT, we should also mention DCT is discrete cosine transform, which is similar to a FFT, basically binning frequencies, right?
Yes, then the more important part is that you don't come up with complex space. If you do an FFT, you have complex values and non-complex and real values, and you don't want the complex values because it's just so much data. We want to do data reduction. So you do that, and what you end up with is basically an interesting hack. So the reason, what you actually want to do is you want to look at the spectrum, but the reason we use Capstrom is because it is even less data, and you basically look at, so what are the peaks in the spectrum, right? Because basically now you're fitting again cosine curves to the spectrum, so you find out what are the peaks in the spectrum, and so you look at way less values. And I don't want to explain this trick here because it's really old. It's like I think 60s or something, and that's what everybody does. And as an academic, I could tell you how bad it is, but the point is, it works. It works, and it's what everybody does. And so I'm while we've been trying, and I have publications on this to replace those features. It's just work. It's really just what everybody does. And
that's
so you
okay.
have these.
We don't judge you here. Dave and I use things that work all the time.
Right. So that's basically the point. So you have these features, MFCCs, and then with those features, usually you match them against these phoneme models. So you try to find out your sort of, this capsule feature, could that be that phoneme or that phoneme? And so you come up with a whole combination of phonemes for that particular region that had high energy. And then you take the language model and say, okay, which of these combinations is the most likely? Because we know the sentences that are most likely in there.
Yeah, it's almost like a paint by, at least in my head, the way it seems like is like you already programmed in, all right, the sentence is, Chris is better than Dave. That's a set of 20 phonemes. Like it's like 20. There's like, and they're all coded, right? Each of the phonemes is coded as, A, F, G, H, I, E, whatever it is, right? And then you go and match against that model. Does that sound right?
Yeah, that's pretty much sound right. So that's the point. And then you come up with all these sentences, and then so we do this on a phoneme level and come up with words, right? So as I said before, you could have 1, 2, 3 as a training, and if you said 2, 2, 3, we would actually recognize 2, 2, 3. So that's the first output, and then the second output would be to match 2 to 3 if you basically ask for that, to forcibly match it to one of the sentences that you were trained in. So that's the whole process.
Got it. So would it, because you're continuously listening, like there's no like a button that you push and go, right, I'm going to reckon, I'm sure your job would be much easier if you got the user to push a button and then speak and then know that's the start of a thing. What is your false detection rate? Like, have you programmed in, a few dozen sentences and then just left it running all day to see, and in an office where people are talking all the time, to see if there's any false output?
Yes. So there's a couple things to say here. First of all, you can do push to talk if you want to. So we programmed the API in such a way that you can either put in a call sign, or you can put in no call sign. Then it will react to any noise. As soon as you raise your voice, it will say, "Oh, that's me." Or you can not do this at all, and you can basically just say, "Don't do any recognition at all unless I tell you." And that means that if you install a button to the Arduino board and then you basically question that button and the button is on, you say, okay, now do recognition. So you can actually do push to talk.
But the call sign is...
Well, in your example, you also show, like the videos that you guys have on the Kickstarter page, you have like a thing that says computer or, what if? Yeah.
That's the thing. I was going to say, like the Siri, like you say Siri, because that's the trigger keyword, so you don't have to search everything else.
It's exactly that. So the
Right.
call sign really helps you get the false triggering down to hardly anything. It's actually, so in our case, the call sign is programmable. You can pretty much use anything, but there are some sort of, if you wish, guidelines. And the guidelines there typically is try to avoid like the 500 most common English words, because otherwise it'll get triggered by just standard conversation, because it's actually really good at picking up the call sign. Typically 3 syllables tend to work really well. So actually Siri, when you use it, it's actually Hey Siri, or Amazon use Alexa, which are words, that are really nowhere near close anything else.
Right.
When we did the robot,
so you can go like, "Hey, you stupid robot."
Well, so actually, with the robot example, we actually just posted. It's called Romibo. So we actually programmed Romibo in there, and Romibo really doesn't sound like anything else. And it picks it up just every single time. It works really well.
What if someone was reciting Shakespeare and they're like, Romibo, wherefore art thou Romibo?
Well, then you're
screwed.
Then you have that problem. So and that's why. So in terms of the second question with measuring the accuracy, you can definitely get into human accuracies with this system. Of course, though, you can also screw it up. I mean, that's the point of being a maker. It can fail. Again, if you make the call sign like to or a, with some of these words that we use all the time, then guess what? It's going to react with it all the time. And also, if you basically program it with 200 sentences, but they're all distinguished in one syllable,
right.
Well, good luck. I mean, that's just
I command that you blank. I command that you blank. I command that you blank.
Exactly.
It's exactly it.
Exactly, that's it. And the point is, though, I challenge you then, if you do that and you complain, to actually try that with a human. Because a human actually is not 100% either.
No.
Right? And of course, the typical things make it worse. If you have heavy accent, it makes it worse. And if you have a lot of noise in the room, it makes it worse.
Or if people aren't paying attention properly, they're not, they're thinking about the next thing they're going to say. Like, we often have that here on the Amp Hour because we're, constantly trying to communicate to people, and we're trying to, we might miss things, and, because we're thinking about
Dave, I have
some
never
question
missed
we're
a
going to ask
sandwich
next.
before.
Oh.
That's what you said, right? Sandwich? It was something about sandwiches?
Sorry? What? What's that, Chris? I was too busy thinking about what I was going to talk about
exactly.
next.
Sandwiches. So I was wondering about this. So what about so obviously it's sitting there monitoring all the time. What kind of power I don't really know. I don't know much about the A13 itself, but what kind of power consumption is it just to sit there monitoring and listening? Because I would think there's no sleep mode. It sounds very active, even if you are just listening for a certain keyword or call sign.
So
what does that take?
We usually say it's 3 watts power consumption in general.
3 watts. You can fly to the moon on 3 watts.
Yes, but
Can you tell the rocket to go there, Dave?
No, that's right.
Well, no. But the point is that it is in fact taking less energy if it's just listening versus, for example, if you're training it. We actually could. Actually, that's something we actually might do. Just actually release an energy profile of this thing. Yeah. Which we haven't done. But we have internally looked at it, and it's actually interesting. It's something that I learned in this project is that you can actually, usually, when you study computer science, we tell students to runtime is important. Well, runtime is important, but when you do small devices, energy consumption is also important. So you can, based on the algorithm you're implementing, the energy consumption changes. And so we actually took this into account a little bit when we created this. And so actually that's something to do, it's a good hint for us to actually release the energy profile for it.
Can people slow it down and trade off response time versus power consumption?
It's a good question.
Not yet.
No, not yet. And this is not the way. This is probably not the way you would want to do it.
It's a stretch goal.
It's a stretch
That's
goal.
Right,
That's
right.
right.
If we hit $50,000 on Kickstarter,
we will have the power consumption. No, but I agree with you, Dave. There's definitely applications where, if let's say you wanted something like
powers
this,
everything, right?
That's going to be battery operated, and you want to change the battery once a year type of thing. Then essentially you'd have to, essentially you would stop the CPU, put it in deep sleep,
You're
if you
right.
will,
Yep.
and then you just keep your analog front end, and whenever you get the right energy,
Over a
you
threshold,
wake up,
yeah,
you wake
bang.
up immediately,
Yep.
you do some processing, and you shut back down. So these are techniques that can be done. We haven't, this is another level in terms of complexity. We haven't gotten there yet.
I was going to say, could you implement like a 2-processor solution where you have a smaller, lower power processor just hooked onto the front end, which recognizes your keyword, and then it wakes up the heavy duty processor to process the, main sentence and things like that? No, there's no advantage
because
there?
essentially you'd be duplicating
You'd be
everything twice,
duplicating
and
the
I don't
effort,
think it'd be
right.
I think just looking at energy level, and whenever you get a
Unless
spike
you had a
in,
fixed keyword, right? Maybe if you had like a fixed keyword, you could program that into a
possibly
low power micro.
So
Possibly.
I think the real way to do this quickly is push to talk, right? So you basically
Oh, of course. Oh, that solves everything, right?
yeah, exactly.
Yeah, right.
Right.
but yeah, I mean, these processors have sleep modes, so I'm sure there are ways of doing it. We've been in the process of solving a lot of other problems so far.
That's the least
I think that this will be
problems.
sort of the next generation afterwards, or if someone has comes with a particular application, we'll be glad to work with them and do that specifically. But I think what's interesting is, once people realize, oh my God, you can actually do this on something that's the size of a credit card, then you start thinking about all the other things you can do with it, and that's I think what makes it really, really interesting. And for us, it's we're finishing the first leg of the journey, and we have a lot of ideas afterwards.
Well, that's okay.
So you guys you've reached your goal, right?
Yes,
but everyone's of course secretly hoping. Is there like a secret goal that you're hoping for? Oh, like we asked for 12 grand, but we really need 50. Otherwise,
No, so
otherwise we're in the poo.
that's so I'm going to tell it as it is. At $12,000, we will be losing money in the process.
Yeah,
we
that's
really
not the problem.
would like to be at 20,000. I mean, to us, this really was. The goal of the Kickstarter campaign was really to engage the maker community, to see what the response was. We've been really getting a lot of really good feedback, questions from people. I mean, we had someone come back to us and say, "Hey, my cousin is paraplegic. He can only make sounds. Would this work?" And sadly enough, the answer is probably not. But I've been working on sound recognition, so it's actually a problem that we know well, and there might be a way for people like this. But this is for us a way to engage the community and make sure that we come up with something that people think, first of all, hey, it's pretty cool, and I could actually use this. And we want to engage them. So part of it is engaging the community. Part of it is marketing, getting our name out. Getting to people to realize that this kind of stuff can be done. And now you can start thinking about what you're going to do with it. We're not in there to make end product. I mean, this is always the difficult part of Kickstarter campaigns, which is not an end product where people can just buy it and put them in their home.
Right.
We're selling a board, which in itself will do nothing unless you're a maker and you're actually going to do something with it. Yeah. One thing I want to mention, by the way, is that we picked Arduino as a platform because there's millions of them out there. It's a great platform, but the basic way the Arduino talks to the Shield is actually via an RS-232 interface. So for people who actually know a little bit about serial communications, and I'm sure there's a lot of people out there, there's no reason why you can't just use the board and talk to any other system. So you could connect to a Raspberry Pi, you can connect to your PC for all I care. Although these days RS-232 is not as common, but it's very easy to use on other platform. And we will be releasing kind of the low-level serial commands, to be able to do all these things at a lower level as well.
Outside the library, you're saying, right? So right now,
the library provides a really nice way, a higher level, to interact with the board. But all the low-level commands will be made. We'll make that available so people can really. I mean, I don't want to call it hack the board because you're not going to be able to go change the software inside, but you'll be able to do some very cool stuff with it that you may not necessarily be able to do with the higher level of tools.
As one last question about software, so I mean, so all this stuff. I mean, you guys had mentioned. Let me just look at my notes here. You had mentioned this MFCC, but like, what is all this written? I mean, like, and you said this is all on a Debian system, but like, is this all Python based, or what is the main languages this stuff is written in? Is it all custom or what?
I like this question because I get this question all the time, and I always tell also, to my students, I tell them, look, a real system is composed of whatever you can take, right? So there's like when people buy a robot, it's like sort of MacGyverism, really.
It's made of hot glue and popsicle sticks. Right?
I mean, when you build a robot, you have to take whatever part fits, and this is the same way. So. This is there is again.
Oh God, he's gonna say it's Fortran, Dave.
No, that is okay. Good.
No,
that is about the only language that is not in there.
Okay.
But it's mostly C for all its thing that's low level. Again, there's a costume kernel and so on. So I needed to go into sound drivers and so on. Yeah. And then there's a lot of Python to glue things together. Which is usually a good way to glue things together.
Yeah, definitely. Yeah.
And there's a lot of shell scripting too. So the other thing is, for example, a board like this needs to start up a little faster than, let's say, your typical Linux boot of a minute. So you need to do a lot of scripting and optimize scripts in this regard. So there's from very low level C programming up to very high level shell scripting and Python and C and C++. And of course, you have your Arduino code that you create a C++ for the library. And then sort of this Arduino-ish dialect for Arduino. So it's all in there. It's multi-language, multicultural.
Right. But what you're mostly saying is that the user won't really have access to, nor will they need to have this kind of access to the lower level programming stuff, or even the high level programming stuff on board. It's kind of just a standalone solution, and you kind of throw it chunk commands through RxD32.
So I mean, basically, I'm saying two things. First of all the Arduino stuff is going to be completely open because all the Arduino stuff is open anyway. The Arduino side. But then also, again, all the open source stuff is open because not only do we have to do that, but it also is absolutely sort of in my intention to always keep open, but it needs to be open. But what I'm saying, though, is it's not that easy for somebody to go just in there and change it because it's such a potpourri of, the real work here is to integrate it in a smart way.
It's interdependencies and stuff, right?
Right, interdependencies. So if you look into it, it's not easy to, it's not like, actually that's the thing, that it might be open source, but it might not be helpful to be open source because you're like in there, it's like, I need to know how to configure a speech recognizer, a Linux kernel, and this and this and this and this. And there's a lot of work. And so that's basically our work. That's basically what it is we basically create a solution where all this configuration complexity is hidden, and just basically all you need to do is do it with an Arduino. And that is basically the magic here, right?
Got it.
Cool. Nice. Well, so how soon is this thing coming out? Because we should probably wrap up here, but I really want to get first thing, I want Dave to get one of these so I can find out what this AGC chip is. And the other thing is I want one of these. I'm building a robotic project right now, and I want one of these for my robotics project. So how long until we can get one of these things?
So right now our early backers will get boards in December. The production boards in December. We will get our own. Yeah. We'll get our own prototypes probably in September. Then we get a qual and do all kinds of great thing to make sure it's all good. But the first 120 backers will get their board in December, and then the rest will be available probably in February 2016.
Nice.
But the engineering, the hardware design is done at this point. We're done with it. We're still doing the some of the Arduino sketch basically is being programmed at this point. The low level stuff is already in there. So as far as risk is concerned, we feel that it's very much under control. It's we're on target basically.
Yeah, and as of this recording, it's 45 left of 124. So 45 lucky people can still get that December board, and I might be one of them.
There we go.
Yeah. Well, this is exciting.
Well, thank you very much for Thank you very much for joining us, guys. I hope your project goes well. We'll definitely link it in.
Great.
Where can people follow you?
So on
Are
Facebook,
you regularly tweeting all this
Yes, so we have
fabulous fountain of knowledge to do with voice recognition?
we have a Facebook page where we kind of
Oh,
update.
boo. We hate Facebook here on the Air.
Yeah, well, you have to use something. I can tell you a lot of things about Twitter. You don't. This is another podcast. If I start talking about Twitter, I have a whole project on. It's called teachingprivacy.org. So we'll talk about that later.
Right, and Facebook is stellar on their privacy stuff.
Oh,
I'm sure.
yeah, they're just the fountain of privacy. Yeah.
I'm not commenting on that either. I agree.
Okay.
But the point is, we have to choose something, and we chose Facebook. And so we have a Facebook page where we basically, this is the first source of information because we put in a lot of personal stuff on there too. Like, when we did the Kickstarter video, we showed some photos of the prep for this and so on. So people see the early stuff, like as it's developing.
what's the link?
On that Facebook page. And the link is
ASR Shield. So
ASR
it's
Shield.
/ASR Shield, all in one word.
Yeah.
Which was not the most obvious name.
So let's actually go there.
You can also
Yeah,
find.
I had trouble finding that. but
Yeah, so
I eventually
ASR
did.
Shield is the project name because when we started, we didn't have a fancy movie. We had an ASR Shield, which ASR stands for Automatic Speech Recognition, and then Shield, right? So ASR is actually the scientific term for all of this. This is automatic speech recognition. So ASR Shield is what it was, before we came up with that name movie.
But you can find us on Kickstarter if you search for Arduino Movi, MOVI. Maybe you can put speech in there.
And we will, of course, have tons of links for the
Great.
user. So,
Great.
Yep.
Thank you.
Okay, awesome.
Thank you very much, guys.
I'm
It's been
looking forward to
fascinating.
this for robotics and everything else. I've always wanted what's the guy's name in Iron Man? The house thing?
Oh, God.
Jay?
I
Is that
watched it
Jay?
the other day.
Jarvis. I want a Jarvis in my
Jarvis.
house.
That's it, Jarvis,
Yeah.
right.
So
Yeah.
if this can give me a Jarvis or even something close, I'm happy.
So by the way, just on that, I tried that call sign and it worked pretty well. So
Okay. All right. Good.
Right.
There you go.
Jarvis for the home. Cool.
All right.
Well, thanks, guys.
Thanks,
for telling
guys.
us all about this speech stuff,
Yeah.
and we'll definitely be checking it out.
yeah, thank you.
Thank you very much.
See ya.
Goodbye.
Bye-bye.
Bye.